Alright, and welcome to today's video. I'm glad you were able to join us today. Let's start with a little bit of a warm-up. So if you would, take a few moments and see what you can do on these 6 problems, and then we'll go over them in just a minute. Alright, so in number 1 here, one of the great mental math strategies is a situation like this, where you're taking a number and multiplying it by a fraction. And so in this case we have 15 times 13 over 5, and you might have thought to try to multiply 15 times 13 first and then divide by 5, but really we have a choice here. We can multiply by 13 first and then divide by 5, or we can divide by 5 first and then multiply by 13, which is going to be better in this scenario, especially if we're trying to use mental math. So 15 divided by 5 I know is 3. And then 3 times 13, let's see, 3 times 10 is 30, plus 3 times 9, or 3 times 3 is 9, gives us 39. So we should get 39. For that one. Alright, last time we met we talked about percentages and working with that. In this case we've got 6% of 11. So that 15% strategy we used last time doesn't really work here. We can use something else. And that's the second strategy I brought up, which is multiplying 6 times 11. Well, 6 times 11 is 66. Obviously 66 is not going to be 6% of 11. Move the decimal, we get 6.6, which makes a lot, still doesn't make sense, right? Because 6.6 is over half of 11. Still doesn't make sense. So move the decimal one more place, and you get 6.6, which makes a lot more sense. All right, so that's going to be 6.66. All right, number 3, starting with 4, add 3 until you reach 50. Really, that's just to practice our number skills and work and adding 3 each time. But also, it should remind you of something we did previously, that idea of repeated addition. So we're starting with 3, that's our starting value, and then we're adding 3 over and over again until you get to 50. So again, repeated addition, we're going to eventually call slope of 3. Number 4, 7 box minus 5 equals 37. So what number times 7 minus 5 equals 37? So hopefully you were able to figure that out, a number of different ways to do it. If we're looking for a number minus 5 that equals 37, then we can think about a number times 7 that's equal to 5 more than 37. So this number here, this part right here, has to be 5 more than 37, so that when we subtract 5, it gets us 37. Well, 5 more than 37 is 42. So this part right here needs to be 42. So 7 times what equals 42? And again, working on our mental math, which involves some of the multiplication skills that we have worked on, maybe in previous grades. So 7 times 6 is 42. So 6 is going to be working there. Later on in this video series, you'll probably see X instead of a box, but really it's the same thing. What value makes that statement true? All right, number 5. Divide 16 by 2 as many times as you can. So 16, 8, 4, 2, 1, 0.5, 0.25, 0.125, and then it gets a little harder from there, right? But I wanted you to start with that mindset, because that's really repeated multiplication. So I know you're saying, well, we divided there. Well, yes, but you could also think of it as multiplying by a half, or 0.5. So we have contrasting ideas here, where here we have that repeated addition approach, whereas here we have repeated multiplication approach. And you can do something similar, like take 1 and multiply by 2 as many times as you can. But in this case, we're multiplying by something less than 1, 0.5 in this case. So lastly here, we have 2 negatives multiplied here plus 1. I want to take a moment and kind of go back to 2 negatives make a positive. We've heard that before, right? 2 negatives make a positive. at least when we're multiplying. Obviously, when we're adding two negatives together, we're still going to get an even greater negative. But when we're multiplying two negatives, I want you to think about it as a negative is switching direction. So when we start with, let's say, this 3 here. 3 is a positive 3 by nature, right? But starting out as a positive 3. So we're moving in the positive direction, so we're at 3, right? And then this negative here means change direction. So I'm changing direction. But then when we have the additional negative from the -4, we're going to switch directions again. So now we're positive. So think of negative as changing the direction. And so with multiplication, if you start out positive and you change direction twice, you're going to be positive again. So that's going to be a positive 12 plus 11 plus 1 is 13. All right. So today's goal is to recognize various function types and see them in real-world context. So we're going to look at a lot of different functions today and the contexts that they come from. Obviously, there are a number of other contexts that these could come from. So I'm just going to give you an example, and then at the end we'll recap and we'll talk about how they differ, and as well as maybe see them all at one time so we can compare and contrast them. All right. So let me introduce you to a few function types. The first one you may have seen before, so let's take a look. So we have, this is called graphing stories, and basically what we do here is we have a graph, and then from there we can try to graph what we're seeing as it takes place. So if we look at our scale here and our units, we're down here along this axis here, we have time in seconds. And then it goes from 0 to 15. So we're looking at what happens over those 15 seconds. And then our vertical axis here is water volume in milliliters. Kind of reminding us of maybe what we did last time when we were filling up those bottles or vases. So we're looking at water volume with respect to time. So how's the water volume changing over time? So let's watch the video, and then maybe you can think about what that might look like. All right, so they were filling up this beaker, and note the beaker is pretty much the same constant width the whole time. And so going back to last lesson, you can probably think about what this graph is going to look like. So let me skip forward here to the answer so you kind of see how your thoughts, maybe you jotted something down, maybe a graph, maybe what your graph looks like compared to this one. So they're going to show the video in the background, but then also show the graph. So assuming we're pouring in at a constant rate, the volume in the beaker is going to be rising at a constant rate. So we started out with 0, and notice the scale here is 100 milliliters. So we didn't reach 100 milliliters until about 2 seconds, and then it kind of continued up from there. This is an example. Go back to it real quick. This is an example of what we call a linear function. So it's a function that has a constant rate. In this case, it's an increasing function. As you'll see in a little bit, linear functions can also be decreasing. But whenever you have a quantity that's increasing or decreasing at a constant rate, and what I mean by constant rate is for every increase of 1 in x, it increases by the same amount in y. In this case, for every second that it increases, the volume increased by the same amount, which might be, I don't know, maybe 40 milliliters or something like that. So that's what I mean by a constant rate, which again later we're going to call slope. So the slope of this one would be 40 milliliters per second. All right, so that's a linear function. So compare that to this next scenario. So I've got a video here. If I can get it to play here. Let me go there. All right, here we go. So this is a map, obviously, but it's going to show these little dots. Each dot represents a million people. And so I notice I've started pretty far along the video. We're already at 1457 in terms of the year. And so you can see the dots, and I'm just going to hit play here, and I want you to think about how population is increasing with respect to time. So is it increasing maybe the same throughout? So maybe is it linear or something else? So I'm going to hit play here and see what you think. So they actually go beyond the current year, obviously, but hopefully you noticed that it wasn't just staying consistent throughout. The beats actually got quicker and were emphasized even more as they went on. And so you might think about maybe the graph of this. So especially if we go back even further in time, it would have been very, very slow. Very slow, just slowly increasing, increasing, increasing. But the rate at which it's increasing is getting quicker and quicker as it goes. So it's not a constant rate. So if you're wondering, it's not a linear function, because it's not staying at the same consistent growth over time. It's actually growing quicker and quicker and quicker and quicker and quicker and quicker and quicker. And the beats are getting faster and quicker and stronger and stronger and stronger and stronger and stronger and stronger. And so this growth that we're seeing here of starting out really, really slow and then increasing really, really quickly is what we call an exponential function. And we're going to take a look at the graph of it in just a bit, but you kind of can see it with my hand here as how it's going to grow really, really quickly. So it's not going to be a straight line like a linear function. All right, let's move on to our next one here. Alright, so this is a video here that we're going to look at, and what we're going to analyze here is the car's distance from us, so from the camera in this video. So this car is going to drive by, and we want to think about what does the car's distance from the camera look like in terms of a graph. So the distance from the camera in terms of seconds. So I'm going to hit the play here, and let's see what we get. So the car's really far away. Okay, it's getting closer. It's getting closer. They're driving at a constant speed. Okay, so they were at the camera, and then obviously they kept driving. So if we think about the graph of this, so they started out really far away, so maybe way up here. Okay? But they started to get closer and closer and closer and closer and closer as time went on, or our x-axis here is time, and then at some point, the car was right on the camera. Right? And then, after that, the car continued to drive at a constant rate, but now away from the camera. So the distance from the camera rose again. And I want you to notice a couple things here. Since the car was driving at a constant speed or a constant rate, this line here is kind of like a linear function. It acts as a linear function. And then also, again, because the car is still driving at a constant rate, we're going to assume, even though we couldn't see it in the picture, we're going to assume it's still driving at a constant rate. So this part also looks like a linear function. And together, they make what we call absolute value. And so the car's distance from the camera with respect to time looks something like an absolute value function. And that's the type of function that we're going to see this year as we move forward in Integrated 1. All right, let's move on to our next function type. So we've got linear functions, we've got exponential functions, and now we have absolute value functions. And let's take a look at another one. All right, up next we have ponies in a frame. So if you think back to the graphing story we did a few minutes ago, we had our axes here, and let's just take a look real quick. We've got time is along our horizontal axis here. So again, 15 seconds, just like the last one. And then look at the vertical axis. It goes from 0 to 10, keep that in mind. But it's ponies in frame. So basically it's the number of ponies we see in the frame of the video as it goes on. So if there's 2 ponies in the frame, then we would have a point right here at wherever we are in time. Okay, so I'm going to play the video and see if you can kind of go along with it and see if you can think about what the graph would look like over time as these ponies enter. I'll even let it play for half speed for you just in case you didn't see something. Okay, so at various points of time there were varying numbers of ponies in the frame. So if you start out, there's just one pony right here. So for these seconds, it looks like from 0 seconds to maybe a half second, there was one pony. So over that whole time span of 0 to half a second, there was only one pony in the frame. And then all of a sudden, boom, all of a sudden at 0.5 seconds, a second pony enters the frame. And so now you've got this second line forming here. And you can imagine that's going to continue, that line's going to continue until a third pony enters, or a fourth, or however many after that. So as soon as it changes from 2, it's going to hop up or down based on how many ponies it is. So I'll hit play here. So we have 2, 2, 2, 2, until about 4.5 seconds, and all of a sudden the third enters the frame. Until about 8.5 seconds, then a fourth one enters the frame. And then all of a sudden, at the very end, he takes away all but one. And so you can see the graph here and how it's increasing with respect to time, but not at a constant rate, right? It's not increasing at a constant rate like a linear function would. In fact, at these time intervals, it's really increasing at a constant rate of 0, if you want to think about it that way. So these put together make up what we call a step function. So, because it looks kind of like steps, right, as you go on. Especially if the amount of time each specific number of ponies was in the frame was consistent throughout. So maybe for like 1 second, 1 was, and then for another second there was 2, another second there was 3. It would really look like a uniform steps. There's no connection here between the lines, and we'll talk about next time why that would mess things up in terms of it being a function. but there's no line here. It's just all of a sudden there's a break, and then there's another one, break, and another one. And so this is what we call a step function, and this is a context in which you might see a step function occur or be modeled. All right, let's move on to the next one. So this is an elevator ride. So if you imagine an elevator following this dot here at the bottom, so it goes up from ground floor to the 10th floor, all the way up to the top, and then it goes back down to the 4th, stays there for a minute, and then that's it. So let's take a look at what, and starting over again, let me exit here. So what do you think the graph might look like with respect to time? So the elevator's height with respect to time. It's going to be a little bit different. So we might be able to graph something here. If we look at our axes again, we have time. We have distance from the ground. So let's take a look at the graph, because it might not be exactly what you think. So the elevator to the 0th floor, and then it increases gradually at a constant rate until it's the 10th floor. Then it stays there for a second or two, and then it goes back down, and it stays at the 4th floor. So elevator speed, we're assuming doesn't change. So it starts at the 0th floor, then it increases at a constant rate, so constant speed all the way up to the 10th floor. Stays there for a moment, maybe somebody gets on, and then its height decreases because we're going down to the 4th floor. But again, with respect to time, it's kind of spread out in this way. So we have increasing, and then it hits the maximum. Remember that word maximum at the top there, and then it decreases at a constant rate, and then it levels off, and it has a rate of 0 there. And so this is what we call a piecewise function. So imagine thinking about each part of here. So this is just a horizontal line. Maybe you remember what those are mapped by, or the function for that. So the equation for this part here would be y equals 0. It's just a horizontal line on the x-axis is y equals 0. This one right here at the top would be y equals 10, another horizontal line. This one right here is y equals 4, I believe it was. And then these two here are modeled by linear functions. So with a slope and y-intercept. And I imagine that this slope here is a positive slope, obviously, because it's increasing. And this one would be the same slope, but negative. And so you can think about, this is a piecewise function, but it's defined by 1, 2, 3, 4, 5 different pieces. So each set of seconds, so in this case from 0 to, I don't think it's 10 seconds, but whatever the scale is here, I need to go back and look at that. From 0 to 10 is modeled by that function. Whereas here it's modeled by a different one. Up there by a different one. And within this time span it's by this one. And this time span is by that one. And so you've got a lot of different pieces here making up this entire graph. And this is what we call a piecewise function, or a piecewise defined function. All right, let's continue. And let's look at our next one here. This is our last one. So we're looking at height, and we're looking at the height of a ball as it's being dropped. So if you look at your axes here, we're going all the way up to 3 feet on our vertical axis, which is height, and then we have 15 seconds again along the horizontal axis.
Go.
So it's bouncing for the first 2 seconds, and then it just is obviously sitting still for the rest. So we don't really need to watch half speed here. You can imagine, what a ball being dropped looks like. So let's take a look at the answer here and see how it compares to what we thought.
Go.
so if we want to think about these pieces here, move this out of the way. If we have these pieces here, each piece popping up here, so let's take this one for example, can be modeled by what we call a quadratic function. A quadratic function looks kind of like a U shape almost, and because it's made up by a bunch of quadratic functions, this is actually be called a piecewise. But I really wanted to hone in on this one part right here and how it can be modeled by what we call a quadratic function. Now in Integrated 1 we don't really get into quadratic functions a whole lot, but I wanted you to at least see it. Just so you have this awareness that there is something called a quadratic function out there, and that's what its graph kind of looks like. It looks like a U almost. Alright, so with that, let's kind of recap here all the functions that we've seen today. So we have a linear function that could look like this if it has a positive slope, this if it has a negative slope, or rate of change, and then of course if it has like no slope at all, we can still consider that either a constant or a linear function. And then exponential can be exponential growth, like we saw in the population, right? It continued to grow, and then it get quicker as we go forward. Or you could have something decaying over time. A lot of things in the natural world decay over time, and so it decreases by a certain percent every year or something. You think about half-life and those kinds of things. So anyways, it decays over time, and it gets shorter, smaller, and approaches zero, kind of like you did in the bell work or the warm-up, where you took 16 and divided by 2 over and over again. You had 16, then you next time 8, next time 4, 2, 1, half, 0.125, and so on. It's very representative of that situation. Absolute value, as we said during that car video with the car driving by, it looks kind of like a V shape. And it could be a V shape opening up, it could be a V shape opening down. So those are some examples of what an absolute value function might look like. And then we have a step function with a video of the ponies, which looks something like this if the height also matches the integer value that it's on at that point. And so it looks like it's a set of stairs, and we call it a step function. Then we have piecewise functions, which are broken up into various pieces based on where you are along the horizontal axis. And so for here to here, it's defined by a linear function, but from there to there, or from there beyond, it's defined by a quadratic function. And so that's an example of a piecewise function. And then lastly, we talked about quadratic functions looking kind of like a U shape. It could be opening down, like it was in the tennis ball video, or it could be opening up, like it is in this video. And we call that really concavity, but you'll get to that later. So it could either be concave up or concave down. Again, we're not going to talk about quadratics too much in this video series or in this course, but again, be aware of it. These are actually in order of how much you're going to see these in Integrated 1. So, for example, linear functions, you're going to see a lot of linear functions. And then exponential, a lot of exponential. You're going to see absolute value, piecewise, and step, but not as much. And then quadratic, probably not much, if any. And so that just kind of gives you an idea of the function types in Integrated Math 1, how they're seen in the real world, and hopefully you're seeing some of these characteristics. Like linear functions can increase or decrease. Same thing with exponential. Absolute value functions have a minimum or a maximum value, as we talked about in the last video. They also have symmetry. Right? If you think about reflecting it on itself down the middle here, it would be symmetric. Actually, quadratics do that as well. So a number of different characteristics that we saw in the last video are popping up again as we look at these different function types. So hopefully we met our goal for today, which was to recognize various function types and see them in the real world context. So maybe in the next lesson you'll see some various graphs and you can identify which one's which. based on their overall look as we've seen today. All right, so that's it for this video. I hope you'll join us next time for defining a function. And what is a function? We've talked about functions today, but what exactly is a function? So join us next time. Thank you.